Hey everyone, in this video we're going to be looking at how to solve simple equations. One thing you should keep in mind when solving equations is that there's going to be a lot of right ways you can do it, but most of the time it's only through a lot of practice that you're going to find an ideal way to solve equations. Now in these simple equations, most ways you could do these are going to be pretty quick, so it doesn't make a huge difference in these cases here that we're going to look at. However, in future cases, when it comes to harder problems, there's certainly going to be usually an ideal method to solve the equations. But the important thing for this video is that you just understand the basic principles about how we can go about solving equations. So to begin, let's take a look at the definition of what an equation actually is. So an equation is a statement that two expressions are equal to each other. If you notice over on the left side, I have this whole list of equations. I have 4 examples that I want to cover here. And each of these is an equation. We have here 200 is equal to 60t plus 95. The number 200 is an expression. It expresses the number 200. And over on the right side, we have 60t plus 95. That's an expression by itself as well. And when you set these expressions equal to each other, that creates an equation. So it's the equality of two expressions. And so the basic idea, so the basic principle is if we're given an equation, like in any of those 4 cases, we can add the same term on both sides of the equation or multiply by the same number on both sides and still have a valid equation. So one thing to notice about equations is that there's going to be 2 sides. There's going to be, if you look to the left of the equal sign, that's going to be considered the left side of the equation. Left and right doesn't matter, but it's going to be considered one side of the equation. And the other side of the equation will be on the other side of the equal sign. Okay, so this expression on the left is equal to this expression on the right. Now let me give you a very basic equation, something that's obviously true here. If we take something like 1 is equal to 1. Now this is obviously a true statement, right? Well, what if we wanted to manipulate this equation in some method? Well, we do have the tools to do that. If we wanted to take the left side, which is 1, and add 3 to it, we could do that as long as we do the same thing on the right side. Okay? So in order to make this a valid statement, if we add 3 on the left side, we have to add 3 on the right side. Similarly, you could do this with multiplication as well. If you multiply the entire left side by, let's say, the number 5, we would have to do the same thing on the right side of the equation to obtain a valid statement. So since we've been doing the same thing on both sides, this is still a valid statement. This is saying essentially 20 is equal to 20, right? 4 times 5 is equal to 4 times 5. So this is still a true statement. And, I mentioned the terms add and multiply, but just as easily we could throw in the terms subtract and divide. I mean, really those come from addition and multiplication. Subtraction would just be the addition of a negative, and division could be considered multiplication by the reciprocal of whatever you were dividing by in the first place. So we could divide just as easily as well. If I take this statement and I divide it by 4, okay, I would have to do the same thing to the right side of the equation and divide by 4. Okay, so this is still a true statement. This is saying 20 divided by 4, which is 5, is equal to 20 divided by 4, which is 5. Okay, still true. Now notice, whenever I manipulated one part of the equation, I was manipulating the entire side, okay? The addition of the 3 was affecting the value of the entire left side, okay? It was affecting everything. And when I multiplied by 5, that was affecting everything on the left side, right? and the division by 4 was affecting everything on the left side. Okay, and that's important to keep in mind. We can't target specific values. Okay, I'll make that a little bit more clear when we're going through problems. A common mistake I see is for students to try to take a particular number like this 3 here and divide by 4 and only target this 3, okay, and then do something different on the right side. So I'll make that more clear as we go on, but it's something we want to be a little bit careful of. You know, when I did this division, it was dividing the entire left side, right? So keep that in mind as we go through the next problem here. Now, some hints to solve these equations. Now, I use the term linear here. Linear means we're just dealing with lines for now. If we were to graph any of these expressions here, we would be obtaining straight lines in the Cartesian plane. Now, one idea, and again, keep in mind, there's different ways to do these. However, you just have to do a lot of problems to figure out the best way for you to do it. One idea you may want to try is to collect all the constant numbers on one side of the equation and all the variables on the other side of the equation. And next up, you want to try to combine like terms whenever possible to try and simplify the problem. Okay. So let's go ahead and take a look at number 1. Let me move this off to the side here, but let me keep it here just so we could keep that in mind. Okay. So number 1 is we want to solve for t. Okay, and what does it mean to solve for t, first of all? Well, to solve for t, and you know, you'd be surprised how many people are unsure of, you know, what this means when solving an equation. You always want to keep the directions in mind. Okay, math is a lot about reading too. It's about understanding what you're trying to do in the first place, and then follow the appropriate steps to get to that final answer. So the reading of directions is very important too, and it's key to understanding what you're trying to accomplish. So we want to solve for t, and what that means is that we want to obtain a statement that looks like this. We want t is equal to, then we want some expression. Okay, we don't really care too much about what this expression is in a math class here. If there's some application, of course, we're going to care what the expression is, but you know, devoid of any applications here, t is equal to some expression. That's all we care about when we're saying solve for t. Okay, so this is going to be the lone t. There can't be any t's over here on the right side in this expression. Okay, our single t is going to be isolated on one side of the equation. So essentially now, when we're solving for t, we're trying to find the t value such that it makes this equation true. Okay, so what value of t will make this right expression equal to 200? Well, if we could get to this point here, then we'll know our answer. Okay, and sometimes, you know, you may be able to do these in your head, but when you get to more complicated equations, it's much harder to do. And again, I mean, these may look simple, but the idea is just to introduce you to how we can go about solving equations in general. And these hints and these strategies, I mean, they're true for, you know, much more complicated equations than this too. So you're going to be using this throughout your math career. So we're going to begin. We're going to try to do some manipulations, and through these manipulations, we're going to try to isolate t. It's kind of like a puzzle in that sense, to try and figure out what you have to do to isolate your variable. Okay, so one thing we could do is we could try to collect all constant numbers on one side of the equation. Okay, so I could try subtracting 95 from the right side of the equation. Okay, And keep in mind now, we have to balance the equation. We have to keep it valid by doing the same thing on the left side. So 200 minus 95 on the left side will give us 105. And on the right side, well, we have 60t plus 95, and then we minus 95. So the positive 95 and the negative 95 will add to 0, so we don't need to write that in. And we'll be left with the 60t. Okay, so now we have 105 is equal to 60t. Now, we don't want 60t, we just want t. Okay, so one way to get rid of this t here would be if I take the right side and I divide it by 60. Right, 60t divided by 60, that's going to give me t. And then we balance this equation by doing the same thing on the left side. 105 divided by 60. Okay, so is 15 going to that? Yeah, 15. Okay, so if we reduce 105 over, well, first let me write this. We have 105 over 60, and this is equal to t. Okay, so we accomplished our mission, right? Because 60 divided by 60, that's 1. And then 1 times t is just t. That's exactly what we're trying to get. We have t is equal to some expression, 105 over 60. And this fraction could be reduced. I believe 15 goes into 105 7 times, and 15 goes into 60 4 times. So that fraction reduces to 7 over 4. Okay, so that's the t value that's going to make this equation true. Now, to further develop an understanding of what we're doing, it's a good idea to check your answer. And we could check our answer by going back to the original equation. Okay, so we have 200 is equal to 60. Now, we just found t to be 7 over 4. So let's substitute 7 over 4 in for t. Okay, so this is the original equation, but in place of t, I put our answer, 7 over 4. We're going to see if we get a true statement. So 200 is equal to, now 60 times, you could consider this 60 over 1, but 60 times the 7 will give me 420. Then division by 4 plus 95. Okay, so 200 is equal to 420 divided by 4 is 105. Okay, so we get 200 is equal to, now 105 plus 95, we get 200. All right, so this is a true statement, right? 7 over 4 is the value that makes this a true statement. If you got something else, like 200 is equal to like 100 or something like that, that's not a true statement. And if you were to get that when you check your answer, you may want to check your answer, or you may want to check your work when checking your answer. But either way, you should be suspicious about something going wrong if you don't get a true statement here when you check your answer. Okay, so that's the first example. That's number 1. Let's take a look at example number 2. So in example number 2, we want to solve for x. Okay, now x is our variable as opposed to t. Alright, so we have 3x plus 20 is equal to 6x plus 2. Okay, so we want to keep these helpful hints in mind for these linear equations. So we want to try to collect all constant numbers on one side and variables on the other. Okay, so let me move all of my variables to the right side, and let me move all the constants to the left side. You could do it the other way around and just perfectly fine. So let's see. So let me subtract 3x from the left side. And the reason I'm writing it underneath the 3x here, this negative 3x, is because I know these two are going to cancel out. Okay. It doesn't mean I'm trying to target a specific piece, but I just know they're going to combine to be 0. So that's why I'm writing it underneath the 3x. And on the right side, I have to do the same thing. Right? I have to subtract 3x. So now my new equation becomes 20 is equal to 6x minus 3x here. It'll give me 3x. Then we have a plus 2. Okay, so that's a bit simpler, right? Now, I wanted to move all my constants to the left side. So this number 2 here is a constant. So I could subtract 2 from the right side so that those two will cancel out. And on the left side, I want to do the same thing to balance my equation, and I obtain 18 is equal to 3x. Okay, so that's great. Essentially, that's combining like terms as well. The 3x and the 6x, those are like terms, and the 20 and the 2, those are also like terms. And so by moving these to the left and the right side, we are actually combining like terms. Now we end up, oftentimes when solving these linear equations, we end up with a situation like this. We're trying to get x equal to some expression. That's the goal, right? So the problem here, it happens very often. We end up with a coefficient that's not 1 in front of the x. Like in this case, we have a 3. And we don't want the 3 there. So we want to divide by that particular number. Okay. A common mistake at this point is people generally remember, they have to kind of divide at this last step to get the x, but they're not sure if they should do, something like dividing by 18 on both sides, which mathematically that's a valid thing to do. At this step, we can divide both sides by 18. That's perfectly fine. However, that's going to lead to something a little more complicated, and we're not going to be able to isolate the x. So again, just through practice, you're going to find out the quickest method to do these things. And in this case, when we get to this portion here, we want to get rid of the 3. Okay, and in order to do that, we divide by the 3. Okay, and we do that on both sides to balance the equation and obtain a valid statement. So on the left side, we have 18 divided by 3, which is 6. And on the right side, we have 3x divided by 3, which 3 divided by 3 would give me 1, or essentially the 1x. So we generally don't write 1x, we just write x. So we have x is equal to 6, right? That's my expression. And like usual, we want to check our answer. Does the number 6 make this a true statement? Well, let's see. We're going to have 3. We're going back to the original equation now, 3. Now, in place of x, let me put what I found it to be, 6. And then plus 20. And this is equal to 6 times, and now in place of x, I'm going to put 6, and then plus 2. Now, is this a true statement? Over here, we get 18 plus 20 is equal to, now 6 times 6 is 36, so 36 plus 2. So on the left side here, we get 38, and on the right side, we get 38. Okay, that's a true statement. So we know our answer of x is equal to 6 is correct. Now, let's see. we want to take a look at a graphical representation of what we're doing here. Just to have a further understanding of equation solving, we could relate this to lines on the graph. Okay, and so when we're solving these equations, we can graph the left side, or graph the left expression, and we could graph the right expression to obtain two lines. And where these lines cross on the x-axis is going to be representing our answer. So let me show you an interpretation here. So for example, I could take 3x plus 20. Oops, where are we? Okay, so I could set y is equal to 3x plus 20. And you could also set it to be the right side, 6x plus 2. Now, if you have a graphing calculator, that's great. You can go ahead and enter these equations into your graphing calculator. You'll obtain two lines, and you're going to see where they cross. But if we don't have one, these are easy enough to do by hand. Okay, so there's our Cartesian plane. We have our x-axis and we have our y-axis. Now y is equal to 3x plus 20. I know this is a line, and to graph a line, we just need two ordered pairs, and that'll do it. So if x were to be 0, I know y is going to be 20. If x were to be negative 5, then we have negative 15 plus 20 is positive 5. Okay. And let me do the other line here. If we have y is equal to 6x plus 2, we could do another table of values for this line here. We have x and y, so the left is our input, the right column is our output. So if x were to be 0, y would be 2. If x were to be, let me say, if x were to be 6, we would get 38. Let me do that value here too. If x were to be 6, we get 18 plus 20 is 38. Okay, so on our x-axis, I'm just going to be counting by 1. So 1, 2, 3, 4, 5, 6, 7, 8. And we're dealing with fairly large output values. So I'm going to go ahead and count by 5s. Here, so 5, 10, 15, 20, 25, 30, 35, 40, 45. Okay, and you want to label a few of these just so people know you're scaling. Okay, so there we go. Now for my first line, I have a point 0, comma 20. Where's that? Oh, let's move left and right 0 and then move up 20. And then we have negative 5, comma 5. So let me move left 1, 2, 3, 4, and 5, and then up 5. So we are right here. Okay, that's good. And so my line, let's see if I could draw a straight line as best I can here. That's why the graphing calculators are nice for this. Okay, so there's my line. That's pretty good. Okay. And so that's y is equal to 3x plus 20. Now, our second line, we have points 0, comma 2. So that is sitting about right here. That's move left and right, or right 0, and then move up 2. And then we have a point 6, comma 38. So that's move right 6, 1, 2, 3, 4, 5, 6, and then up to 38. And that's 40. Okay. Let's see, it's about right there. See, if I drew this line better, it should be hitting that point. Okay, but let's see. So we have our graph going up here, hitting this point right here. Okay, now this first line, if it looks like it's crossing over here, but really they should cross over here. So it's a little hard to do by hand. It's a little hard to be this accurate. But essentially, where these lines are crossing on our graph will be at x is equal to 6. Okay, around this point here. Okay, let me do that. There we go. So around that point there is where these lines should be crossing. Okay. And that's the answer we found, right? When x is 6, we found these two expressions to be equal to each other. When x is 6, we got a height of 38. So that's where they should be crossing. On the graphing calculator, obviously, it's going to be much more accurate than I could be here. So if you have one, I encourage you to check that out. Now, that's the graphical representation, and it's a good thing to keep in mind, Same thing when we have this situation here. We could graph it if we wanted to. But for the most part, these are easy enough to do by hand, so we don't necessarily need to go to the graphing calculator. But, it's nice to know how to do things in different ways. So here we have 2/3 x plus 1/2 is equal to 11/2. Now, just because we're working with fractions, it doesn't change the basic principles of equation solving. These fractions here, you should treat them just like any other number, okay? So to begin, keep these hints in mind. We want to try to collect all constant numbers on one side. So the numbers 1/2 and 11/2, those are constant numbers. So I'm going to try to move those onto the same side. So I'm going to subtract... Oh, what are the directions here? Solve for x. I forgot to write that in. We want to solve for x here. So now we want to move this constant number 1/2 to the other side. So we're going to go ahead and subtract 1/2 from the left side of the equation. And that's going to eliminate the positive 1/2 here. And I'm going to do the same thing on the right to balance the equation. So now we have the new equation, 2/3 x is equal to, now 11/2 minus 1/2 is going to be 10/2. Okay. So let me just rewrite that in a different way. We have 2/3 x is equal to, instead of writing 10/2, that just simplifies to 5. So that's what we have at this point. So now when we're trying to solve for x, again, you want to keep in mind we're trying to get x is equal to, what? Okay. Now the problem here is we have a 2/3 times x. And in our previous cases, what we did was we divided by the coefficient. Okay. Now that still holds perfectly true. Let me show you two ways to do this. So let me star this portion here. And let me show you a couple different ways how you could isolate the x here. Now, first thing you could do is, since we want to eliminate the 2/3, we can divide the left side by 2/3. Okay? Now that makes sense, right? 2/3 divided by 2/3 will be 1. And we'll get x is equal to something. So if I do that, I'd do the same thing on the right side. I would divide by 2/3. Now, so 2/3 divided by 2/3, that equals 1. So we have 1 times x, or just x, is equal to. Now 5 divided by 2/3, let me do this off to the side here. Instead of dividing by 2/3, that's the same thing as multiplying by 3/2. Remember that? So instead of dividing by a fraction, you could multiply by the reciprocal of that fraction. And this is much easier to do than this here. Okay, multiplying fractions is easy. We get 15/2. Okay, so All I did was I took this statement and moved it over here just to simplify it. So we get x is equal to 15 over 2. Okay. Now, that's one way to do it. Now, let's go back to this spot here. We have 2/3 x is equal to 5. And we'll check our answer in just a moment. We have 2/3 x is equal to 5. Another way to do this, so this is a good strategy to keep in mind. Now this left side here is being divided by 3. Essentially, if I write this a different way, this is the same thing as 2x over 3 is equal to 5. Okay. This statement here and this statement here, these are the same things. Okay, because you could think about x as being x over 1. So the x would be with the 2 up in the numerator. So we have 2x over 3 is equal to 5. So the whole left side here is being divided by 3. And what we've been doing up to this point is we've been using inverse operations to eliminate numbers where we could. Like when we have multiplication going on here, we did the inverse operation of division to get rid of this number. When we have an addition going on here, we do the inverse operation of subtraction to get rid of this number. So now we have this division of 3 going on. So if we apply the inverse operation of multiplication, then we may be able to get rid of this 3. So if I take this left side and I multiply it by 3, this 3 and this 3 are going to cancel each other out. Okay, so I'm going to do the same thing on the right side. I'm going to multiply by 3. So now 3 times 2x over 3 will just be 2x is equal to 15. And then lastly, we want to get rid of this 2 because we're trying to isolate x. So we divide the left side by 2. We do the same thing on the right. So we get x is equal to 15 over 2. Okay, so these are two different ways to think about it. I honestly think most people would do this second method here. Because, I don't know, I think a lot of students try to avoid working with fractions whenever possible. So instead of dividing by 2/3, they take this problem in 2 steps, and which is, there's nothing wrong with that. It's a perfectly valid way to do it. They'll multiply by 3 first to get rid of the 3's, and then divide by 2 to get rid of this 2. Okay. Whereas with this here, dividing by 2/3, that helps, that solves for x in a single step, whereas this takes 2 steps. But you know, it's a minor difference between these two things here. As you really are doing the same thing, because when you divide by a fraction, you're doing this. You're multiplying by the reciprocal. If you notice here, what we actually have is a multiplication by 3 and a division by 2. That's exactly what we have going on over here. Okay, so now is that answer correct? You may want to go back and check. We have 15 over 2, right? So I'm running out of space here, but let me give myself some space in the middle. Oops. Okay, so inside of this box, we'll check the answer. So we have 2/3 times, let me just do this. We know x is 15 over 2, or we think it is 15 over 2 if we did everything correctly. And we have plus 1/2 equals 11/2. Okay, so if we simplify this left side and it comes out to equal 11/2, we'll know we did it right. Well, 2 times 15 is 30, and 3 times 2 is 6, and plus 1/2. Well, instead of writing 1/2, I'm going to have to combine these fractions. So instead of writing 1/2, I'm going to write 3 over 6. Same thing, right? And we're saying that this is equal to 11 halves. Okay, so this 30 over 6 plus 3 over 6, we add the numerators to get 33. Keep the denominator. And let's see, is that 11 halves? So 3 goes into 33 11 times, and 3 goes into 6 2 times. So that fraction does indeed simplify to 11 halves. So 15 over 2 is the correct answer. We do obtain a valid statement when this is plugged back in. Okay. And lastly, let's take a look at the last problem here. We have negative 7x plus 3 is equal to 4x minus 5. And let me hide those helpful hints here. Let's try to do this without the hints. See if we can remember what to do. Okay, so we want to try to move our constant numbers to one side and our variables to the other side. So our constant numbers are positive 3 and negative 5. So let's see. So let me do this. Let me subtract 3 from the left side of the equation, and we'll do the same thing on the right. So we obtain negative 7x is equal to, so the positive 3 and the negative 3 cancel out, right? And then we'll get 4x. And negative 5 and negative 3 will combine to be negative 8. Okay, so now we want to try to move our variables to the left. So I was moving my constants to the right. I want to try to move my variables to the left. So here we have a positive 4x. So to get rid of it, we would subtract 4x. And we do that from both sides. So now we obtain on the left side negative 11x is equal to negative 8. Okay, because those are gone from the right side now. 4x minus 4x essentially cancel to 0. So now we have negative 11x equals negative 8. And again, when we are trying to solve these equations, we want x is equal to something. But this negative 11 here is messing things up. So what we want to do is divide by that negative 11. Okay, negative 11 divided by negative 11 will leave us with 1x. And we want to balance this equation by doing the same thing on the right. So we should obtain x is equal to, now negative 8 divided by negative 11, I know negative divided by a negative is a positive, so we should obtain 8 over 11. And last thing, you may want to check your answer. So let me go over here and just write check answer. So we have negative 7 times, now x is 8 over 11 plus 3, and we're going to see if this is equal to 4 times, instead of x, we're writing 8 over 11, and minus 5. Okay, so negative 7 times 8 over 11 is negative 56 over 11, and then plus 3. And we want to see if this is equal to, now 4 times 8 over 11 is 32 over 11, and then we're subtracting 5. Okay, so to combine these two numbers, we need a common denominator. Right now this is over 1, and right now this is over 1. We want an 11 to be here, so we would want to multiply that by 11, and we do the same thing in the numerator to balance this fraction. So notice how this balancing acts. I mean, it's really a major theme throughout algebra, right? Balancing things to obtain an equivalent statement. And over here, we want to do the same thing. to have a common denominator, we want this to be an 11. So we multiply that by 11, but we balance the fraction by doing the same thing to the numerator. So now our new statement becomes negative 56 over 11 plus, now this will be 33 over 11. We want to see if this is equal to, now this is 32 over 11, and this will become 55 over 11. So negative 56 and a positive 33, we get negative 23, and this is over 11, and 32 minus 55 will also give us negative 23 and over 11. So that is a true statement. So we know x is equal to 8 over 11 is indeed the correct answer. This is the value that will make these two statements true, or it'll make this equation true. Okay, so that will do it for this video. I hope you enjoyed it. Be sure to practice lots of examples for solving equations, because it really takes a lot of practice to get used to this idea, okay, before you're really comfortable with this. So I will see you in the next video.